Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
This video is part of a series of videos on how to draw axial force, shear force and bending moment diagrams in beams. Previous videos analysed this simply supported beam. There's a knife edge support at A, a roller support at C, and the beam carries 2-point loads. If you'd like to watch these videos, click the link on the screen. This video analyses the same beam, only this time the beam carries a uniformly distributed load, a UDL, that runs the whole length of the beam. So, let's get to it. As usual, we will start by finding the reactions. Draw a free body diagram bubble that cuts the beam away from its supports. The purple lines represent the cuts, and these cuts expose the unknown reactive forces. If all this makes little sense to you, click the link on the screen to find out more about cuts, free body diagram bubbles, and all sorts of cool stuff. Now, draw everything in the bubble, that is, the beam, the UDL, and don't forget to draw and label the unknown reactions exposed by the cuts. The next step is to apply the equations of equilibrium to the free body to find the unknown reactions. We're dealing with a plane structure, and this means there are 3 equilibrium equations available to us. These equations are commonly expressed as horizontal forces must sum to 0, vertical forces must sum to 0, and moments about any point must also sum to 0. Starting with horizontal equilibrium, we see that HA is the only horizontal force, and because horizontal forces must sum to 0, HA must be 0. It's not rocket science. Taking moments about A shows that VB is 196 kilonewtons, and summing vertical forces shows VA is 84 kilonewtons. Replace the unknown beam reactions on the free body with these numerical values. And if you want to see a more detailed video on finding reactions, then click on the link on the screen. In general, plane beams and frames carry axial force, shear force and bending moment. These forces arise in the structural members in response to loads applied to the structure. Dr. Jim thinks of loads and reactions as external forces, and he thinks of axial force, shear force and bending moment as internal forces that arise in response to the external applied loads. Note that Dr. Jim is using the word force in a generic way, as it includes external applied moments and internal bending moments. Anyway, that's enough about what Dr. Jim thinks. Let's get on with the problem in hand. To proceed requires a sign convention for the internal forces in the structural elements. And here is a graphical representation of the sign convention we use. The boxes represent a thin element cut from the beam. Note that tensile axial forces are regarded as positive. Shear forces that try to spin the element counterclockwise are regarded as positive. And bending moments that put the top face of the beam into tension are regarded as positive. In other words, hogging moments are positive. The next step is to figure out what's going on inside the beam. To do this, we must cut the beam to expose the internal forces. So draw a free body diagram bubble that cuts the beam x1 meters from A. Now draw the free body defined by the bubble and label the unknown forces exposed by the cut. Writing down the equations of equilibrium for the free body shows the axial force A is 0. The shear force S is 20x1 minus 84 kilonewtons, and the bending moment is 10x1 squared minus 84x1 kilonewton meters. And here is a reminder of Dr. Jim's rules for calculating the internal forces in beams. Always assume the unknown internal forces to be positive until proved otherwise by the arithmetic. Always explain what you're doing. For example, state vertical forces must sum to 0, and that vertical forces acting upwards will be regarded as positive. Do this to make your checking your calculations easy. Besides, it's good manners to do so. Always take moments about the cut to find the unknown internal bending moment. Note that the moment or turning effect of a UDL about a point is the same as the moment of a single force equal to the total value of the UDL acting at the center of the UDL. If you would like a more detailed graphical explanation of the moment of a UDL about a point, click the link on the screen. Well, that takes care of what's happening between A and B, and because we are going to draw axial force, shear force and bending moment diagrams, we need to record the results. This is best done in a table with 4 columns. The first column contains x1 values tabulated at 2 meter intervals. The other columns contain numerical values of the internal forces. Next, we need to find out what's happening between B and C. Notice that Dr. Jim has chosen a free body diagram bubble that isolates the beam to the right of the cut. This produces a simpler free body than the alternative. Using a free body diagram bubble that isolates the beam to the left of the cut will result in a free body that includes both reactions as well as the UDL. Draw the free body diagram for everything inside the bubble we're using, remembering to include the unknown internal forces exposed by the cut. Now apply the equations of equilibrium to determine algebraic expressions for the unknown internal forces exposed by the cut. Horizontal equilibrium shows that the axial force is 0 between B and C. Vertical equilibrium demands that the shear force is minus 20x2 kilonewtons. And summing turning effects about the cut shows the expression for bending moment is plus 10x2 squared. Draw another table, record the results, and the analysis is complete. All that remains is to draw the axial force, shear force, and bending moment diagrams. These diagrams are simply graphs of the internal forces in the beam drawn on an outline of the beam. The tables show there is no axial force in the beam, so only shear force and bending moment diagrams will be drawn. Draw a grid to facilitate drawing the shear force diagram. The vertical scale is minus 100 kilonewtons to plus 100 kilonewtons. Now draw the structure to form a baseline for the diagram. The tabulated results for shear show that shear force is minus 84 kilonewtons at A, plus 116 kilonewtons just to the left of B, minus 80 kilonewtons just to the right of B, and 0 at C. And we know that shear force varies linearly under a UDL, so connect these points with straight lines. Note that the reactions are effectively point loads and they cause steps in the shear force diagram. Step heights are equal to the magnitude of the reactions. Now to the bending moment diagram. Here things get a bit tricky. Inspection of the expressions for bending moment shows that bending moment varies parabolically under a UDL. This is an important finding. To draw the bending moment diagram, we will again use a coarse grid, only this time the vertical scale goes from minus 200 kilonewton meters to plus 200 kilonewton meters. Draw the beam to establish a baseline for the diagram. Plot the bending moment values from the results tables on the grid. Then put numerical values on the maximum sagging moment, 176 kilonewton meters, and on the maximum hogging moment, 160 kilonewton meters. Note that the values on the bending moment diagram are unsigned. We simply draw bending moments on the tension side of the beam, and, according to our sign convention, bending moments that cause tension on the top surface of the beam are positive. In contrast, the values shown on the axial force and shear force diagrams should always be signed. Next, Connect the dots with curves that approximate to parabolas, and finally pretty up the bending moment diagram. It's unlikely that 176 kilonewton meters is the true maximum sagging moment in the beam, and being engineers, we need to figure out what the maximum moment is. Any thoughts? I hope you're thinking calculus, but don't stress, it's dead simple. First, write down the expression for the bending moment between A and B, 10x1 squared minus 84x1. Now differentiate the expression to get the slope of the bending moment diagram. When the slope is 0, the bending moment is at a maximum. So the maximum sagging moment occurs 4.2 meters from A. Plugging 4.2 meters into the expression for bending moment shows that the maximum sagging moment in the beam is minus 176.4 kilonewton meters. And plugging 4.2 meters into the expression developed for shear shows that the shear force is 0 when the bending moment is at a maximum. This turns out to always be the case. This is an extremely useful finding. This example has added 3 important new tools to our toolkit for drawing axial force, shear force and bending moment diagrams. Shear force diagrams are sloping straight lines under UDLs. Bending moment diagrams are parabolic under UDLs. Maximum bending moments occur at points of 0 shear. These laws apply to all beams and frames, both statically determinate and statically indeterminate. And that concludes the analysis. If you would like free printable annotated notes for this video, then swing by Dr. Jim's website at drjimstructures.com. In the next video in this mini-series, Dr. Jim will analyze the beam using LinPro, a free lightweight frame analysis program. To watch the LinPro analysis video, click the link on the screen. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.